Every year, KUKA does the Innovation Award since 2014. Here at Hannover Messe 2017, we are live from the show floor. We wanted to give you guys a sort of overview of all the different 5 finalists that are here this year, showing off their research projects. It's been a kind of a tough 8 months for them to get it ready for the demos here. So without any further ado, we got 5 to go through. Let's start with the first team here. You guys are from USC, correct?
Yes, we're from University of Southern California, Los Angeles.
And what is your research project? What are you guys doing here?
We're working on a solution for surface finishing applications. As we all know that 3D printing or additive manufacturing has become very popular nowadays.
Yeah.
All the aerospace companies like NASA, SpaceX, everyone is adopting this technology. But what don't people talk about is the dark side of 3D printing. Say a metal part like this takes about 20 hours to print. But to actually use it, you need about a week of post-processing, and which is done completely manually. And we're building a solution where you can actually, polish, sand, or clean any new part every day for any geometry or any material.
When I was talking with you guys earlier this week, I mean, we've been doing this now. We've all been here for 5 days. I think we've been burning the midnight oil. We're a bit tired. But it seems like, the thing you're trying to address is this last step in the process when you're manufacturing things, to machine away the surfaces or to polish away the surfaces. And that right now is a very manual thing, right?
Exactly.
So what you've done is created a 2-robot system that can handle that, but without human intervention, correct?
Yes, that is correct. But human is always in the loop. It's a collaborative system where human makes the high-level decisions or does the creative task, and robot takes away the tedious and time-consuming tasks, and also takes away the health hazards.
Yes, so tell me a bit how it's able to model the thing and how it's able to get in those intricate, small, confined spaces.
Right, so we use our advanced planning and machine learning algorithms to actually determine how the 2 robots can collaborate and plan and actually finish the part, because for different material and tool, you'll need different sort of settings. So there our algorithms actually play the role, and given any new part, we can actually finish the job.
Great, okay, so another thing I saw you guys had that's pretty fun, it's not a critical aspect of this, but you say the human's still in the loop?
Yes.
How does the human get notifications?
Oh yeah, that's a very cool feature. So Bruel, during this demo, we are running a lot of demos throughout the day. Bruel is getting full with all SMS on his smartwatch.
At the end of the day, I'm getting around 500 texts on my watch.
So they're getting notifications to their smartwatches when there's something that the human needs to do here. Okay guys, thanks so much. I really appreciate you giving us a short overview. There's so much more to discuss, I'm sure.
Yeah.
If you want more info, we have a highlight movie online for these guys. It's the Advanced Robotic Finishing Team from USC. Thanks again. We're going to move on to the next booth.
All right, thank you.
So walking over here, these next guys have developed an interesting system for robot and human collaboration, installing heavy parts, correct?
Yes.
So first off, tell me who you guys are, where you're from, and what your research project is.
Yes. So we are Loris, Tito, and Alessio. We are from Italy, from the Institute of Industrial Technologies and Automation of the Italian National Council of Research, and we are working on this human-robot cooperation application.
So what are we seeing behind us? I mean, this looks like a sound stage or something, but it's not. It's a simulated aircraft cabin, correct?
Yes, exactly. So here we are simulating the installation operation of a netbox component inside the aircraft cabin. And this kind of project is very related to an European project we are involved in that is called the Eureka project.
Okay, so we're looking over here. Your colleagues are lifting the bin into place. The words I came up with were kind of zero-gravity installation, meaning that as the human guides the box into space, it's not much effort. So you're taking the strain off of lifting heavy parts away from the human, correct?
Yes, it is like this. So now Alessio is going to lift these heavy components. The robot doesn't know which is the weight of the component and the tool, but Alessio is still capable to move around the component along this constrained trajectory in order to complete the assembly installation.
You were telling me earlier, normally something like this with a heavy part like a bin, it takes maybe 2 humans to lift it up and another one to install it. So here, not only you're taking the strain away from heavy lifting, but you're also making the process more efficient, correct?
Yes, correct. So we are trying to both improving the flexibility of the application and the ergonomy from the human point of view. So we are trying to reduce the stress for the human and also increasing the productivity in the aerospace industry.
So tell me about these QR codes we see up here at the top. What are those for? I mean, how's that working in the process?
Yes, so these QR codes can be identified by the camera we have on the robot and effector, and in particular we can use these QR codes in order to define the path the robot is moving along, and in this way we calibrate the system with respect to the robot.
Great, and actually this Flex Fella, this is a KUKA Flex Fella, you could move this anywhere and it would still be able, based on lining itself up with the QR code, to be able to do the same process, right?
Yes, so the idea is that during the mounting of this kind of components, the operator can move along the fuselage of the airplane, and head track by head track can do the same operation without any high effort.
Great, thanks so much. We're going to move on to the next team. I really appreciate your time. That's a nice explanation. Good luck in the contest.
Thank you.
Okay, moving on to our friends from the DLR here. You guys have a very interesting research project, but first off, could you tell me who you are, where you're from, and what it is?
So, hello, my name is Hannes Höppner. I'm from German Aerospace Center, Institute for Robotics and Mechatronics, and this is the first airbag for robotic end effectors.
But, you know, when I first heard about this, I thought airbag like, you know, in a car. But it's not really like that. It doesn't react so much as it's protecting the humans from the sharp objects that might be in the end of the robot, correct?
Yes, this basically, so you have the robot itself, it's safe for human-robot collaboration, but now you have the sharp-edge grippers and also the sharp-edged workpieces. And the problem is that you cannot get rid of these sharp edges from the workpieces, so when you transport them, you can only drive very slow. That is the problem.
So it's a real problem that many people are facing as collaborative robots like the LBR-EY here get implemented in workspaces.
Yes.
You know, the robot can move faster, but because it might have sharp pieces in it, it can't move as fast. So the airbag is meant to make the workpiece and the gripper safe, so it can move fast through space and increase throughput, correct?
Yes, this is correct. He's every time before he starts moving fast, he's inflating in less than 1 second, and also when he wants to deploy the object, he's again deflating again, also in less than 1 second. But also this airbag has pressure sensors inside, so we can detect whether the airbag is correctly inflated. But it allows for some interaction with the airbag. So the pressure sensors, they detect whether there was a collision or not. We can further interact with the robot.
One thing I saw earlier that's really cool is that you can actually use the airbag as an input.
Yes.
So it's like a button. You squeeze it and it can do something,
Yes.
right? So, or squeeze it twice and make it do something else.
Yes. Now you see, if I squeeze the robot, okay, the airbag, the robot detects that and can act accordingly to it. And also, if I now have my hand here, then you see the airbag, because of this pressure sensors inside, is able to detect this collision.
Great, that's really cool. This one I like a lot. I'm still wondering, you know, application in the real world. You guys got to take it from this to a real product, and I know that's your intention. So I wish you all the best luck in the competition.
Thank you.
Thanks for the overview. Again, the DLR guys with the airbag. And let's move on to the next guys. Hello, how are you doing, Sina?
I'm fine.
So could you tell me a little bit about who you are and what your project is?
So I'm Sina and my colleague Nadia. We are PhD students from EPFL Lhasa, Switzerland.
Nice. So what is the research project here?
So we are proposing a control architecture to collaborative multi-arm and humans. As you can see, Nadia is moving the big object toward the arms, and the arms are moving in coordination with each other such that they can grab a big object from Nadia.
So in the real world, I mean, this is a problem that many people face. You know, the human starts the process and the robot finishes it because it's wanting to lift the heavy parts, keep that from the human, also, you know, be able to do it more accurately, for instance. So how do the robots coordinate with themselves and also with the worker?
So based on the position of the object, we calculate if the object is going toward the arms or not. And if the object is going toward the arms, we have started to coordinate the robots with each other, and after that we coordinate the robots with the object.
So there's a 3D model essentially that's being made, or is it something else operating here?
So it's based on the control architecture of the system. We just read the position of the object.
And I see cameras up around us. What are those cameras for?
These cameras are for finding the position of the object. As you can see, we have markers on the object, and based on these markers, we can find out if the object is moving toward the arms or not, where are the grasping position, and what is the orientation of the object.
And why do I see two different kinds of grippers here? We have a human-like hand and then also sort of a standard robotic gripper over there.
So in general, we wanted to show that our architecture is not depend on the specific gripper, and we can use any type of gripper, and we can use it in the industry also.
I also see that we have this part, and we also have another part over there. So you guys have been going back and forth. Why did you decide to bring two different parts here?
So we just wanted to make emphasis on the fact that we are not specified for that one specific type of the part, but we can use any type of the big part, and we can use our application for any part.
Great, okay. So these guys with it's a sort of heavy lifting assistance, I guess. Wish you all the best of luck. We're going to move on to the next team. Thanks a lot.
You.
Okay, we're going to sneak back through here to these guys. This is one of the most impressive Innovation Award demos I've ever seen. What you can see in the background is a drone, but they're not going to call it a drone. It's an aerial manipulator. Could you guys, before we get into what we're seeing here, could you tell me who you are and what your research project is all about?
So my name is Antonio Franchi, and I am a CNRS researcher in France, and I am leading this group of people, which is an international group, which counts in the CNRS, the INRIA in France, and University of Siena in Italy, and Seoul National University in South Korea.
So that's quite a global audience. I mean, you guys are all over the world. It's already an impressive feat to coordinate research across the planet like that. So, I mean, obviously there's people standing around watching this every time it goes in the air. It's really impressive to look at. What is the research project trying to achieve?
So our goal is try to show that with an heterogeneous team composed by a ground manipulator and a flying manipulator, we can achieve much better results and perform operations that are otherwise impossible with the standard ground manipulators.
So I guess from what I was talking with you earlier this week, the robot, if it has a long thing in its arms, it's got too much torque on it. So the robot can't lift that up. The drone is meant to go to the end of the long piece and lift it up in coordination with the human. We see some operation with the human down here. Is that, what are we looking at there? Are you calling it telemanipulation, correct?
Yes, exactly. So here we implement what we call the shared control. Shared control means the system has its own autonomy. At the same time, the human can interact whenever he or she wants, and at the level the human decides. So the system can be either fully autonomous or fully teleoperated. And this is done in a bilateral way. It means the human operator receives also a feedback, a haptic feedback, using this force feedback device, which gives a lot of what we call situational awareness. It means the human is more involved and knows better what's going on the robotic side.
And I mean, a lot of people say, cool, but why? What's the application?
So the application, we cannot see them now, but in the future we can think, for example, to having these kind of systems composed even by more than just one aerial manipulator and ground robot. For example, employed in search and rescue scenarios after disasters, when you have a collapsed building or you want to, for example, remove debris that are inaccessible via ground or too dangerous to access by ground, you can use the cooperation of aerial manipulators. But we can even envisage in an application in the future inside the factories of the futures to do a logistic cooperation, and also the future of construction of buildings, tall buildings or tall structures like bridges and so on and so forth. So the applications are really just up to our imagination.
Well, there you have it, guys. You have 5 really spectacular Innovation Award competitors. Wish them all the best of luck. Tomorrow, about 11 in the morning, Germany time, we'll be bringing a live award ceremony to you, and we'll see which one of these 5 actually wins the award. It's a €20,000 prize, so there's some high stakes. Thanks a lot. We'll see you tomorrow.